Welcome to our lesson on electric fields. We'll look at the work that Millikan did to determine the elementary charge. After J.J. Thomson had discovered the cathode ray, or electron, and its charge-to-mass ratio, it was the work of Robert Millikan that led to the measurement of the actual charge, or the elementary charge. Once this was determined, the mass of the electron could also be found. Millikan's experiment began with two charged parallel plates, as shown below. Any charged particle within the electric field would be affected by both an electric force, which is up or down depending on its charge, and a gravitational force downward. A negative charge would experience an upward force. A positive charge would experience a downward force. Either of these two charges, positive or negative, would experience a gravitational force down. Millikan used a perfume spray bottle, or an atomizer, to create a fine mist of oil droplets, which he directed into the electric field as shown below. As the oil drops leave the atomizer, they rub against air molecules. Some acquire a positive charge, while others, which Millikan was more interested in, acquire a negative charge in the same way that clouds become charged as they move through the atmosphere. Millikan was interested in these negative charges because if an oil drop is negative, it will be pushed up by the negative plate and attracted by the positive plate. The oil drop will also experience a downward force due to the effects of gravity on the oil drop's mass. If each of these two forces are balanced, the oil drop will experience a net force of zero. When Millikan was able to observe an oil drop that was suspended, he knew that the upward electric force, Fe, was balancing the downward gravitational force, Fg, resulting in zero net force and zero acceleration. Since Fnet is zero for the suspended oil drop, we know that Fe is equal in magnitude and opposite in direction to Fg. And therefore we can write electric force up is equal to gravitational force down. The electric force is equal to the product of the electric field strength times the charge on the oil drop. The gravitational force is equal to the mass of the oil drop times the acceleration of gravity, 9.81 meters per second squared. We can solve for the charge on the oil drop by rearranging the formulas for electric and gravitational forces and solving for Q. We divide both sides by the electric field strength, and we're left with Q is equal to the gravitational force, mg, divided by the electric field strength between the two plates, E. If both the potential difference and plate separation are known, then the electric field strength across the two plates can be determined by using electric field strength is voltage supplied by the battery divided by the displacement between the two plates, or the distance, which is d. To determine the mass of the oil drop, you could use the following two formulas for density and volume of a sphere. Taking the density from the manufacturer, Millikan was able to measure the radius of the oil drop. Density is equal to mass divided by volume. To get the volume, of course, Millikan had to observe the oil drops and estimate their radius. Once he knew the radius, he could calculate the volume. Once he knew the volume and the density, he could calculate the mass for each oil drop. Following this process, Millikan suspended and measured many oil drops and found the value of Q for each oil drop using the equation on the right. Millikan had a small magnifying lens mounted on the side of the electric field apparatus and was able to isolate and measure hundreds of oil drops. He was able to determine the charge for each oil drop and found an interesting result. All of the values of the charges were multiples of a very small number. Each of these values, it appears, were multiples of 1.60 times 10 to the minus 19 coulombs. So Millikan assumed that this was the smallest possible charge. Each of the many, many values that he found appeared to be multiples of this number. This is the lowest common factor of all of the charges Millikan found. This is now known as the elementary charge, and is the charge on a single electron, negative, or a single proton, positive. Now that Millikan had determined the smallest, or elementary charge, he was then able to determine the mass of the electron. Remember that J.J. Thomson had determined the charge to mass ratio to be 1.76 times 10 to the 11 coulombs per kilogram. Millikan was easily able to rearrange this ratio and substitute his value for Q. Solving for mass, Q over the charge to mass ratio, substitute 1.6 times 10 to the minus 19 for coulombs for the charge, divide that by Thomson's charge to mass ratio, and we get the electron mass at approximately 9.1 times 10 to the negative 31 kilograms. We still accept this as the electron's mass, although most textbooks say 9.11. This is very close.